My name is Thomas Clouse. Along with Jonathan Crabtree, we designed an unmanned aerial vehicle, or UAV, for the National Forest Service to aid in location of lost hikers at national parks. The National Forest Service has identified an increase in an event involving lost hikers. The National Forest Service, or NFS, has noticed that hikers tend to rely on the GPS in their smartphones for directions more than focusing on map reading skills. This becomes an issue when satellite coverage is lost, and then they end up lost as well. The NFS says finding lost hikers quickly is the best way to increase their survival rate. The NFS was looking to explore options for using remotely piloted vehicles, or unmanned aerial vehicles, UAVs, to help find the lost hikers quickly and more efficiently. They believed that a slow-moving, smaller vehicle operating at a lower altitude would have a better chance at finding a hiker, as well as being found more rapidly than a search party or rescue team that would be on foot. We were tasked with identifying performance metrics for the UAV to meet the needs of the customer. For the NFS, they did not list specific requirements for the UAV, however, they did have certain tasks that they wanted it to be able to perform. This vehicle needs to be able to search for hikers in day and night conditions and be able to fly at low altitudes through the mountains. It also needs to be able to be transported easily. We must take this information and use it to find specific factors and how the UAV will be used. The customer, the NFS, needs solutions for remote piloted drones that will assist in the search and rescue efforts of lost hikers. They're looking for a vehicle that can operate in low mountain terrains and that can cruise at less than 3,000 feet. A system is required that can be easily transported so that they can transition from one search area to the next. These operations need to be carried out at any time of the day or night, as well as any time of the year. Finding lost hikers fast is a vital key part to survival and morale at parks. Some limitations and restrictions would be the environmental conditions, or weather and temperature. These operations will need to be carried out at any time of the year, so this means that the vehicle needs to be able to withstand both the extreme temperatures of summer and winter. It will also need to be able to go through rain and snow. We need something that can track the hikers on foggy or smoky terrain, and since we are tasked to make the UAV that works on a low terrain, it is important since fog settles on low mountains during early mornings. The operation also needs to be able to be carried out at any time of the day. The vehicle will need night vision capable cameras. Thunder and lightning, high winds, and heavy precipitation may have major impacts for the safe return of lost hikers, and they need to be considered when designing the UAS. Some operational scenarios include needing a drone that can go into deeply forested areas without losing contact with the hub. We're going to need more than just optical sensors and cameras here. We can also add night vision and infrared cameras, as well as a heat sensor, which could be helpful to detect body heat. The range of the UAS cannot be understated. It is imperative that the UAS be able to remain airborne for long periods of time to offer more continued search time. Longer operating time means less time spent flying back and forth to search areas, refueling, and recharging. The payload capabilities were not directly mentioned by the customer, the NFS, but it is possible to have a UAS large enough to carry a payload, which at the operator's will could dispense a first aid kit or water to lost persons. If so, the size of the UAS will be a factor. As far as global positioning, the UAS will need a highly accurate GPS system to give first responders precise details of the whereabouts of the hikers, and for ease of operability, the range of a fixed-wing UAS could be substantially larger than that of a rotary-wing aircraft. So let's break down each of these parameters that we compared our two aerial vehicles to. The first being the ability to operate in a temperature range of 0 to 100 degrees Celsius. According to a study from the University of Colorado and the National Center for Atmospheric Research, between 0 and 100 degrees Celsius is the typical operating temperature of a UAV. In addition, it mentions how a UAV might still be able to function outside this range, but not at optimal performance. Further on, it reinforces what we understood, that extreme temperatures have a negative impact on individual components of the UAV. Some examples discussed in the study that supported our decision on the scoring include the effect of extreme temperatures on batteries and electronics performance, the impact on different materials used in the different parts of the UAV, and the effects of the temperature and air density, which directly impacts the aerodynamics of the UAV. Due to the variety of weather conditions in the forest, depending on their location and season, we understand that this requirement was essential to meet the needs of the National Forest Service. The next, be under 48 inches wide to enable convenient loading. Mobility in a forest can be rough, and tree density can fluctuate depending on the type and size of the trees. For that reason, it was necessary that the NFS required a UAV that could be transported from one location to another without much problem or change. Unfortunately, the platforms available to us were a bit larger than we would like. The fixed-wing UAV requires a location that has enough clearance for it to take off and requires a launcher, which would add to the amount of equipment required for the UAV operation. For the octocopter and the rotary wing, the total width of the arms and the rotor respectively affect their transportability. The deciding factor would be if they can be converted to a smaller dimension for it to be easier to transport. We believe that the octocopter had the advantage due to its folding arms. In Figure 1 we have images of a similar model with folding arms. We can obtain UAV models with features like folding arms, removable wings, or folding rotors. We could potentially have a higher requirement score on the grading matrix, which would provide a wider range of platforms available to meet the NFS standards. Next is the need to be able to fly for 10 minutes straight without refuel or battery swap. The endurance of the flight could be affected by weather conditions and the number of movements and corrections the UAV must make itself. The power supplies available and the fuel alternatives are more than enough for flights lasting 10 minutes or less. Communication range needing to be 500 meters or greater. While in direct line of sight, all UAVs demonstrated good communication with the ground control system, or GCS. Dense foliage and hills might cause a loss of line of sight with the GCS, and this could be fixed with antennas with repeaters along a designated area. But since a lost hiker could be lost anywhere in a forest, it's not a very practical idea. Antennas might also disrupt the national habitat of creatures and vegetation in the forest. This is one of the reasons we needed a portable UAV, so it may be moved from search area to the next, knowing that the range of the comms can also help in the search of lost hikers by dividing the search area into sections where the UAV can reach. And finally is the need to be able to equip an infrared camera to detect the lost hikers. And a hiker could be lost for hours, even deep into the night. Foliage can be too dense to look underneath the canopies, and for that reason, optical cameras are just not enough. Infrared cameras can detect heat sources, making it easier to find a hiker through the trees or night cover. All UAV models tested can be equipped with infrared sensors. Now, as you can see, they were very close in performance, and honestly, any of the designs could meet customers' needs. However, the best option was the Octocopter MK1. The Octocopter MK1 is what our final design will be. The Octocopter MK1 that we decided to go with as our final design worked great during the flight test. This UAV can work in most temperatures and climates, allowing it to function year-round. The infrared sensor and normal camera allow for target acquisitioning during day and night, and the GPS allows for the relay of the exact location of any lost hiker once it's found. The manual control allows them to determine exactly where they want to search instead of it being on a set flight path. The laser altimeter allows it to navigate through low-level terrain and vegetation with no issues. The EPA powerhouse of 10,000 allowed for a battery life that greatly exceeds the 10 minutes, and it can quickly replace to allow for more flight time. The communication range is up to 1,750 meters depending on the terrain, and the UAV can be packed up quickly and moved to another location. During flight tests through Yosemite, we noticed that the greater range that you get from the control station, the less you can go through more dense terrain and vegetation. There's a simple fix to this, and we highly suggest that the NFS adds in multiple antennas/relay stations throughout the area, which will allow for uninterrupted service of the UAV throughout their areas of operation. In conclusion, the NFS was looking for a UAV that can operate all year, day or night, at low altitudes through mountain terrains and can be easily transported. We took this and turned it into technical requirements. We needed to design a UAV that would be small enough to transport and that could operate in temperatures from 0 to 100 degrees Celsius. The UAV would need GPS, infrared camera capability, laser altimeter or LiDAR, 1,000 meter range minimum, a good battery life, and a minimum of 10,000 mAh battery capacity. We took this to the drawing board and came up with two variations of a rotary wing UAV, and we put them through extensive testing and realized that they both were great options and would meet the customer's needs. With them being so close, we had to create a grading scale, put the two models side by side. After grading the models, the scores were close, but the Octocopter MK1 did have a slight advantage. We decided to present the Octocopter MK1 that we created due to its slight edge it had over the other models. This UAV greatly exceeds all requirements that the NFS has. Our suggestion is to accompany this amazing UAV be antennas and relay stations throughout the operating area to allow for clearer signal while operating at further distances. When lives count, time is of
Loading
the
into
essence. You can unleash
Streamlabs,
the
my name is
Octocopter
Jonathan
MK1.
Crabtree, and this is our Group 2 flight test comparison between our two systems. First we load in, we'll choose our chassis. You have plenty of options. This is what we went with. First we'll see D1. This is the Gannett rotary wing. Fuel will be gas, generator, manual control for maneuverability and self-control whenever we can control from the ground. IR with gimbal. This is going to be crucial in both of our systems. Laser altimeter for altitude, RPM indicator, dipole antenna, EPA powerhouse, batteries, gotta have fuel for the gas engine, GPS module, temp sense, IMU. For both systems we chose portable man just for mobility purposes. Notice the weight or the payload is capable of carrying. This is a bigger, slightly larger system, so keep that in mind. Comm range is 1400, which is pretty good. Electrical and the endurance 64 minutes, slightly over an hour of flight time. Loading in. Let's try to simulate finding a missing hiker. First we'll put an antenna down, choose our starting point. Let's fly. With this, we'll take off. We'll choose FLIR. FLIR allows us, gives us the ability to see IR heat signatures, which with a person missing out in the woods, the dense forest, as you can see here, we've located something of a heat source. More likely an animal, however, if that was a hiker, we would have just found him within seconds of takeoff. So we can go over, fly to them, and due to the GPS that we have on, we are able to relay the coordinates, the lat longs, and then we can get emergency services to come. Notice the distance kind of got out of range, but if you go up in altitude, the system comes back. It's just a little bit of trial and error. But this, so we have this here. Now, the reason we went with both rotary wing is because we are able to sit and be stationary, and we can continue to monitor until help arrives. So this is the D1. Back to assembly. Again, notice 1400 comm range, 64 minute of flight time. But it comes at the cost of using fuel with a gas engine. So that's another thing, that's just something to keep in consideration. Come up, let's load D2. Another rotary wing. You'll notice it's much smaller of a profile. A quarter of the flight time. .500 meters, so a third of the distance you're able to travel. However, with the portability and the portableness and the mobility of this system, you're able to transport it much easier without the requirement of a large trailer or a larger vehicle for that matter. This one we have electric motor, no need for fuel, just batteries. Easy, come back, swap batteries, go back out. Manual control again, same sensors, same antenna, same battery, GPS. Again, we go in, let's try and find a hitchhiker with this system. Put an antenna down, same location, same waypoint, and fly. As we take off, we'll swap it back again to FLIR. And right away, again, you're able to point out the heat signatures, which makes these systems that we've created crucial in assisting the Forest Service with finding lost hikers. They're very mobile, very user-friendly. Lat longs give you the extreme accuracy of locating a person once you find them with the FLIR, like we have here. You can zoom and you can monitor their location, and you will never lose them. Back to the assembly. Again, this is group 2, My name is Jonathan Crabtree. My partner is Tom Clouse. Thanks for watching.